Alright, so we're going to start this video talking about different types of emissions from atoms and molecules. And the first one we're going to talk about is absorption and emission spectrums. And these are caused, both absorption and then and emission. And these are caused by electrons in orbit around the nucleus basically moving around. And so this first started being discovered where people were looking at different kinds of light and they were breaking it up using prisms, using all kinds of different things, diffraction gratings and stuff you can do this with. And what it does is it causes just regular old, let's say we had white light. I can't really do white, so I'll put yellow down here. But you have just white light, pretend this is white, okay? White light comes in, goes through some kind of filter or something, and then it spreads out, and it separates based on its wavelength for visible light, and red and, orange, just that old Roy G. Biv, red, orange, I hate to use it, but yellow, green, basically then just we'll do it just a little blue, and then we'd have violet over here, some purple color basically, and it would spread out like this. And so what people found was, instead of having this nice pretty continuous color thing, like a rainbow where there was no breaks, they found that there were all these lines that were occurring inside it. So when they looked at this and they looked at this spectra, what they found is, all right, it was nice and it was pretty and it was red here, and then it would just go along and there'd be this black line in it, and then there would be, you come along over here and there'd be some space and it's just orange and it's yellow, and then suddenly another black line or two or something like that, and you'd have all these kind of randomly spaced just black lines where it was just no light coming through. Some were thicker than others and all kinds of stuff, and this was kind of a problem. Of course, you have to imagine, because I don't think I can color it in well enough, that this is red. It's like a rainbow. It just kind of goes from red all the way over to purple through here, but with just gaps in it. And then people found that this was a problem when it was just pure white light coming in. And then they found that there was the reverse that could happen, that they could have something. This one would occur in some situations, and then in other situations it would be all black everywhere. But then there would be a few nice colored lines, and they even found that sometimes these colored lines would match up with what the black ones were, and I'll get to talking about that soon, of why some of this matched up. But there would just be these distinct colored lines here that would show up, and they'd be in the same place that the black lines would be, but not always. I mean, it depended on what was creating the light and everything like that. They all created different things, and people struggled with this for a long time. They didn't really know what to do with it. You had these missing lines and full rainbows, and then you had, if you did it a different way, you'd get these just colored lines, potentially where the missing lines were if it was dealing with the same materials, and the rest would be all black in there. And it turns out that this this part here where it was missing lines, this is an absorption. That's an absorption spectrum, and then this was an emission spectrum. And so what they found was these emission spectrums, when they would take like one type of material, like hydrogen or something, and they would get it to give off light, and they found that it would just give off only certain colors of light in small little areas of it, not in big wide ranges. And then they found that if they shone light of all colors through hydrogen, like through another material, then it would give black spots, black lines, where the colored lines would have been, if instead of that thing had been absorbing it, it had been emitting the color. And so this was very perplexing, but eventually an answer was kind of happened upon, and it required a new way of thinking. Basically, the idea was you would have this nucleus in here. That's our nucleus, and then you would have these electron orbitals around it. And these electron orbitals, in order to solve this, They had to be specific. There was only certain values that could occur, and other ones weren't allowed. So you'd have this. This could be like, this could be, the first orbital and the second and the third and the fourth on out. And the idea that actually allowed for getting this was that the energy released had to be equal to any different changes in these orbitals. So, for example, if you had an electron in this second orbit, if you got it to give up its energy, if you got it to release light, it would drop down to this first orbit. And then the amount of energy in that light would have to be, conservation of energy would have to be equal to the amount of energy between those energy levels. And the same thing right here. Like you could have one out here in 4 that could drop down to 2. It doesn't always have to just drop down 1, or it could drop all the way down to 1, but they could just drop, or it could just drop to 3. And then however far it dropped, if you calculated the energy difference between those orbitals, that's what photon of light was given off. And the different photons of light with different energies would give you different colors. So essentially, if there was a color, like say right in here, that there was no energy equivalent difference between these shells, then this atom could not ever actually give off that light frequency. It couldn't get off that energy of light. For example, if it tried to give like half of this energy to here, it couldn't do it because an electron couldn't go down half an orbital because there's nowhere in here for it to actually sit and exist. So it wouldn't happen. And you'd get all these just discrete photons and these discrete colors that would come out for these different discrete energies because the electrons themselves were in discrete orbitals, and they really just couldn't do anything in between. And then the same thing for the absorption. If I send every frequency of light through this, well, in order for it to be absorbed, say for an electron down in this first orbital, for it to be absorbed, this photon has to come in, here comes this photon in. Well, when it hits on here, the electron, if it's too small of an energy, like that can't get this electron up to this next energy level, then it's just going to pass right through and not be absorbed. So the only energy levels it can actually absorb are ones that will get it exactly to one of these orbitals. So these absorption lines would just match up nicely with the emission ones because those were the only kind of photon energies that it could either give off or interact with. So it could absorb one and move out to here, or one could be here and move out to there, and all different kind of things. They could jump in and out, but only at certain places. And of course, these two would have to match up because those are the only energy levels that can be possible. Now, why do they have these specific energy levels? That's kind of a whole different topic there. You have to start worrying about wave interferences and all kinds of stuff. So we'll worry about that at a different time. But it turns out that these, if you made a few assumptions about this, that you had these discrete energy levels, these discrete orbitals, that as you went further out, these orbitals got higher in energy. Basically, they went from negative to less negative to less negative, all the way out to where you get to infinity. When you get out here to infinity, just kind of like that gravitational potential energy, this would go to an energy of 0, and then that kind of gets less and less more negative as you go towards it. So this would be like, I think for hydrogen, it's like negative 13.6 would be that first energy level in here. And in electron volts, sorry, it would be that smallest energy level in here that it can get down to. And so it would just decrease as you went in and increase as you went out. And it did this in according to a nice little equation that would tell us the energy of the photon. And it was the first big discretized kind of equation where we needed to do this. And it's E equals HF, where E is the energy of the photon, F is the frequency of that photon of light, and then H is what is called Planck's constant, very, very famous constant, and it has a value of H equals 6.63 times 10 to the negative 34, so it's a very small number, joule seconds. And it's this that links energy to photon frequency. And so this is a very, very important equation. It's basically the energy of a harmonic oscillator in quantum mechanics, that E equals hf. You can also combine it, if you do a little bit of math, you can combine this with our old wave equation that says that the velocity of a wave is equal to frequency times wavelength, which is ultimately was just velocity is distance over time, where wavelength was distance and frequency was 1 over time, because remember frequency is hertz, which is a 1 over a second. And if you combine it with this, you turn this into the wave equation for light, where the velocity has to be c equals f lambda, then you can go in and replace this. You can say that frequency is equal to c over lambda, and if you plug this in, you get E equals h c over lambda, and you could use it in that form, or if you wanted to actually work with wavelength, you could isolate that and get h c over E, and that would tell you the wavelength for a certain energy photon, and you could go in and work with it that way if that's what you were working with. All right, so this is basically what happens when you get emission from atoms and from molecules, where the emission comes from the electrons jumping around. But this isn't the only kind of emission that can occur. Okay. Well, one more little thing. Remember this equation. Know this one. This one down here, it's pretty useful, but as long as you remember your old wave equation thing here, which you should, you can derive that one. So there's no real sense in doing this. This is something you can just put these two things together and get this last one. And you should get kind of used to doing stuff like that. You got to be able to mix different equations together and do that kind of stuff. But this isn't the only kind of emission we can have from an atom. We can also get emission from the nucleus, not just the electron changing energies, but we can also have energy shifts and things being lost from the nucleus. And then this would be called radioactive decay. All right, this is a kind of different kind of emission, and from this we need to know a couple definitions. The first, you need to know what an isotope is. An isotope is basically the same element but with different numbers of neutrons. So you could have something like uranium, and you could have uranium with more or less neutrons. It's to be uranium, it has to be the exact same number of protons. So for an isotope, it's the same number of protons. In other words, the same element, but different number of neutrons. So you may have heard of something like uranium-235 and uranium-238. Those are the first ones I could think of. Well, one has 235 protons and neutrons in the nucleus, and the other has 238. Since it's both uranium, it's the same number of protons, which means that one has 3 more neutrons than the other. The 238 has 3 more neutrons than the 235, and they are said to be isotopes of each other. You can get the same sort of thing with hydrogen. Just a single proton is technically a hydrogen atom. It would just be an isotope of the regular hydrogen atom that you would expect to be 1 proton and 1 neutron. Okay, so you don't even have to have anything else with it. Basically, just a proton is an isotope. It's basically just a hydrogen isotope. So it is a hydrogen atom, even with no electron and no nucleus or no neutron in the nucleus. The next thing is nuclide. This word I don't really like to say that much. Basically, this is a specific, a certain nucleus that has a specific number. So this is a specific nucleus with a specific, no, I'm using the word specific there, specific number of protons and number of neutrons. Okay, so if I go back to like that uranium-238 and uranium-235, those would be different nuclides because one would have uranium-238 would have a specific number of protons and a specific number of neutrons that added up to 238, and the 235 would have a specific number of protons and a different specific number of neutrons. Oops, I forgot my E there. That would add up to give it a different thing. So this would be just the difference, the specific isotopes essentially that have a specific number of certain ones there. But I guess it doesn't always have to be isotopes because it could also be a difference between elements. Because if you change the number of protons too, it could be like the difference between hydrogen and helium or iron or anything like that. But it's not just like with an element where all you care about is the number of protons. For this nuclide, we care about the number of protons and the number of neutrons in there and what exactly they are. And if you change either of them, you're changing the nuclide for it. Okay, so now what kinds of radioactive decay do we have? And we basically have three types. We have three types of this radioactive decay. The first type is called alpha decay. Alpha decay. And this is when an alpha particle is released from the nucleus. An alpha particle, and it would look like this. It has four protons and neutrons in the nuclide, and it has in the nucleus, and then it also has a positive charge of 2. It's got 2 protons in it. Well, if you're sitting there thinking, well, wait a second, what has 2 protons in it? It's a helium atom, and that's essentially what this is. It's a helium atom. And so this helium atom is essentially ejected from the nucleus, and then since these protons are lost, in order for this to be ejected from the nucleus, these protons are lost, this would actually change what element you had there. And this could be, something, it would drop it down by 2 protons and change its element to whatever is, 2 protons below it on the periodic table. So you would just go and look and see, well, that's what it became essentially. So this is the first type. It's just a helium atom being ejected from the nucleus. Okay, so I don't know. Could I try and draw that? You have some nucleus, a bunch of protons and neutrons all clumped together. Right? I don't know how many I'm drawing here. They're all clumped together in the nucleus, and then suddenly, a moment later, you have this helium atom with 4 of these ejecting and going away, and then your other nucleus is just smaller by that same amount, just a little smaller, while this goes and flies off wherever it's going. And you have some sort of decay and some sort of energy release there, depending on how much it was. The next kind is beta decay, beta particle. And the first kind of beta decay we have to talk about is an electron. It's an electron being emitted from the nucleus. Above, we talked about electrons shifting shells around, and if they went out to this, go back up here real quick. If they went out to this infinity energy level, if they went out to this infinity energy level, then they would have just been ejected and they escaped, right? If they shot out to that one, but that would then release one of these photons for it. But down here, we're talking about an electron being emitted actually from the nucleus. And when this happens, it's called beta decay. And it's when you essentially have too many neutrons for it to be stable. You have like more neutrons than are stable with the number of protons you have. And when this occurs, there's a few things that have to happen. One, you have to conserve charge. And if you have an electron being created and emitted from a nucleus, well then that's a negative charge, which means the nucleus has to gain 1 positive charge to cancel it out. So in order for it to gain 1 positive charge, that neutron that emitted it essentially becomes a proton. So in order for this to happen, a neutron has to become a proton. It changes into a proton. And this also changes, just like before, just like this other type of alpha decay, it also changes what element you had, because now you have one more proton than you had before. So you went down, you went -1 in neutrons and +1 in protons, which changes your element and makes you some sort of new isotope of whatever element you changed into that has one more proton than what was there before. Now, when this was first discovered, it was also found that there was a missing amount of momentum here, that momentum didn't seem to be conserved. And since it was pretty well known that momentum had to be conserved if all of our rules of physics were to stay consistent, uh, and so there was nothing else that was seen. There was nothing else that was found that had any kind of charge or anything to it, because if it had charge, we could deflect it and try and detect it. And so the only way to conserve momentum was to predict the existence of a new, small, and neutral, since there was no other charge that could be in it, this already conserved charge, a small and neutral particle. And it turns out that this particle, which was very hard to detect, was the anti-neutrino, all right, the neutrino. And now the neutrino was named after this because it basically means little neutral one. And so this new particle was predicted, and it was a while before it was actually verified, but it had to be there. It was a small, tiny little thing that was really had very little impact, except it served to conserve, it just was there to conserve that little bit of missing angular momentum. And it turns out that not only can we have an electron emitted from the nucleus, oh, I'm sorry, and the antineutrino has a little symbol, looks like this. It's like a little curvy V. It's the Greek letter nu, and it has a little line over it, which is the anti part, the antineutrino. In a minute, we're going to talk about the neutrino, and it's the same symbol, but it doesn't have the bar above it. So it's that little curvy V, the nu symbol in the Greek alphabet. Well, there's another kind of beta decay, and it's when you have an anti-electron. And this anti-electron is also called a positron. And this positron is the same as an electron, except it's positively charged. It's a positively charged electron. So when this occurs, you are ejecting a positive charge. And if you're losing a positive charge from the nucleus, then there must be something there to cancel it out, which means you have to essentially have something losing that positive charge and becoming neutral. Because remember, in the nucleus, there's only positive charges. There's only protons with positive charges. Neutrons have no charge. So if a positive charge is leaving the nucleus, you must lose a positive charge in the nucleus. So in this reaction, you have a proton giving up its charge and becoming a neutron. And this would change your element as well, and it would drop it down one, because now you've lost a proton. So you'd look at your periodic table and you'd go down one in the number of protons to what the new element would be. And the same sort of thing has to apply here. There was still some of that missing momentum, and so there had to be another particle, and it turns out that particle was just the neutrino. Not the antineutrino, just the regular neutrino, and its symbol was just that curvy V, just the Greek letter nu, no bar over it, because the no bar means it's just a regular. With the bar, it's the antiparticle. It would be opposite in charge, and they're very similar, and we'll talk more about those later. But that's our second type. So our first type was alpha, our second type was beta. Both of these change what element we have, and then we have a third type, and it's called gamma radiation. Now this is the really bad stuff. This is what created the Incredible Hulk, right? At least as far as the comic is concerned. Please don't go irradiate yourself with gamma radiation given the opportunity, because most likely you won't turn into a Hulk. You would pretty much get yourself killed. So don't do that. This is the really bad stuff. Essentially, this really usually occurs as the nucleus resettles itself. As these things, it goes along a lot with these kind of decays, because stuff is ejected and then everything else has to resettle back down, because that's what things in nature like to do. They like to go to their lowest potential. They like to settle way down. And so this would settle down into its lowest energy form that can, and as it settles back down, it's going to give off some of that energy in order for that to happen, and it'll give it off in the form of a really high energy and dangerous type of photon. Okay, that's what a gamma particle is, and there's lots of these out in outer space and everything. It's these gamma particles, and they're given off, and it has a high amount of energy. And this is the kind of thing that, like damages your DNA and stuff like that, and it does a lot of damage to living things. So this is the bad one. So again, we had our alpha, which was just a helium atom ejected. We had a beta particle, which was either an electron or an anti-electron ejected, along with a little neutral friend, either the antineutrino or the neutrino. And these both change what element we're looking at. Here, we have a gamma particle given off, and the gamma particle, it is neutral. It doesn't change what element it is. It doesn't take any charge with it. It's just a little photon, and it takes away a good bit of energy with it, for the levels we're talking about. But that's gamma, and I just kind of scratched right through it there. Here's our gamma decay, and then the last thing is, well, what causes this radioactive decay? And it turns out there's really just two main things. What causes this? I can move this down further. And the causes of these radioactive decay, well, there's two main forces that happen inside the nucleus. Well, first off, the nucleus is a bunch of positive and neutral things. There's no negative charges in it. It's all protons. And so you would think that, as we learned from electricity and magnetism, these protons, they would repel each other. So that is the case. They don't want to be together. So what in the world is causing to hold them together? It turns out that is called the strong nuclear force, the strong force. And this force is a lot stronger than that Coulomb repulsion that would be between the positive charges. It would try and bind them together. It pulls them back together. But even though it's a lot stronger, why doesn't it just crunch all the positive charges together, all the nuclei out together? It only works over very short distances. And I'm talking about short distances like within the nucleus. So in order for this to actually take over and be the strong thing, you have to get nucleons, you have to get protons and neutrons close together before this force has an effect and makes them stick together. Okay, so it's the strongest force there is, but it happens over very, very short distances. So it doesn't rule the universe. It only rules down in the nucleus. And this holds them together. Well, how does that cause our radiation? Well, it doesn't. But eventually what can happen for your helium decays and things like that, where protons and neutrons are actually getting ejected up here with our alpha decay, well, essentially what happens is if it gets too big, if the nucleus gets too big, it starts to become unstable. So you get those really heavy elements like uranium, and they're very radioactive. And the bigger ones, they're more radioactive. They don't live very long. They break apart and they decay because the nucleus gets just too big and the stuff gets too spread out. As the nucleus gets, you have a nucleus that fits in this side and it fits in this. Now everything, and it just gets bigger and bigger and it starts to fall apart. There's a video they did on Mythbusters where they tried to roll a big giant ball made out of Legos, and this ball was like taller than they were. It was a real giant big ball. Now, if you stick just a few Legos together, they can be kind of hard to pull apart. They really get stuck together, and you could probably throw it on the floor and stuff, and two Legos, they're not going to break apart. But now take something like thousands and thousands, if not a million Legos, and build them into a big giant ball, and then try and do something with it. Well, the weight of the Legos trying to hold themselves together could become so great that it would just start breaking apart. Pieces would fall off of it. And that's what happens in the video the Mythbusters did. And I have that video. I'll try and show it to y'all sometime. It just starts to fall apart and it breaks apart and it does not stay together very well, and it breaks into smaller, more stable pieces. And so that's from the strong force trying to hold that nucleus together. The next one is the weak force, and this is a force that's responsible for our beta decay. It's our beta decay, the beta particles, the Greek letter beta. So the beta decay. and it's responsible for that. This weak force is weaker than the strong force. It's weaker than it, but it acts over greater distances than the strong force. So this can actually, that's really the two main things you have to know about it. It's weaker than the strong force, but acts over greater distances, and this causes beta decay. Okay, this actually causes that to emit those electrons and stuff. That's the force that's thought to be responsible for that. So we have the strong and the weak forces acting inside the nucleus, and they cause our radioactive decay. Now, I say this is a greater distance. It happens. The weak force acts over a greater distance than the strong force, but it's still a short distance compared to things like electromagnetism and gravity. Those act over seemingly infinite distances, no matter how far apart they are. Especially gravity acts over great distances. Electromagnetism seems to act over great distances. It's just it kind of cancels itself out with its positive and negatives. But these two, they don't really have anything to cancel themselves out, but they act over short distances. But of course, this is longer. The weak one is a longer distance than the short one. All right, so that's all I have to say about our little introduction here for different types of decay. And thank you. We'll move on to something else.